Welcome to the next video, everybody. Today we're going to look at the universal Galois deformation ring. Let's get into it. So why Galois representations? I'll give you two reasons. We want to study continuous group representations rho from pi to gln of A, where A is some coefficient ring and pi is profinite. We're primarily interested in the case that pi is gks for some number field k and some finite set of primes s of k. Go back to my very first video on chapter 8 for definitions there. Let's consider for a moment residual Galois representations, which are Galois representations rho bar from gks to gln of k, where k is a finite field. There are only finitely many of these for a fixed k, s, and a middle k, and each one only requires a finite amount of data to build. So these are excellent objects to study instead of studying these more complicated objects rho. Once we have a residual representation, we can consider the whole class of Galois representations, which are deformations of rho bar. So lifts. If rho bar is absolutely irreducible, any member of this class will come from a single tidy package, which we'll call the universal deformation, as we will describe soon. In particular, we'll obtain large amounts of information just by looking at a single special universal representation into gln of A for some coefficient ring A. Okay, this ring, which will later be called R of rho bar if it exists, is unique up to unique isomorphism by usual category theory nonsense. And it will be called the universal deformation ring of rho bar. Okay, it's not clear that this actually exists though. I mean, this is a pipe dream, but if we can't actually construct this ring, then we can't really use it to do anything, right? If it doesn't exist. Reason two, if I have the universal deformation ring R of rho bar for a given rho bar, we might then ask which quotient rings correspond to Galois representations with certain nice properties. Equivalently, we're wanting to find the closed subschemes of the spectrum of R of rho bar corresponding to these properties. So properties might include modular or fixed determinant or something like that. Okay, for us, there'll be the type D deformations that we talked about in chapter 1 of my notes. Trying to find these points in the universal deformation space, which is this spectrum here, is conjecturally nothing more than imposing certain local conditions at the ramified primes of rho bar, which is neat. And then the whole point, like the upshot here, is that Wiles and Wiles-Taylor actually proved this conjecture for certain nice conditions and certain local conditions on ramified primes as part of their proof of semi-stable modularity. So that's where we're going with this. Here's the big theorem. Let n be a natural number and let rho bar from gks to gln of k be absolutely irreducible. So take some absolutely irreducible residual representation. Then there is a universal coefficient ring, R equals R of rho bar with residue field K. So it's actually in that category C hat of A from earlier. And a universal deformation, rho U from GKS to gln of R, of rho bar to R, which is universal, in the sense that if you give me any coefficient ring A at all with the same residue field K, and any deformation rho from GKS to gln of A of rho bar to A, there is exactly one coefficient ring homomorphism H from R to A inducing the identity map on residue fields, so it's a coefficient ring homomorphism, for which the composition of rho U with the induced map, gln of R to gln of A, which we'll also call H, is rho. So in other words, you have rho bar down here, right? So it's best to look at this diagrammatically. So gln of K. So what I'm saying is there's like a big boy way up here, a big lift, rho U, to some gln of some R, such that if you give me kind of any other lift, rho, to gln of A, then all of these triangles commute. All these diagrams here commute. That's what I'm saying. Okay, and another way of saying this is that the functor D sub rho bar is representable by R. If you're not familiar with that language, it means that if you take D sub rho bar and evaluate it at any coefficient ring A, this is the same thing as the WK algebra maps from R to A, where W of K is the ring of Witt vectors of K. Okay. So the proof is in Mazur's original deformation theory paper, and he also gives a cute proof of this when n equals 1 there using class field theory. If you want the actual proof, you can again see Mazur's paper, but you can also consult Gouvea's arithmetic of p-adic modular forms, or his deformations of Galois representations, or the Diamond-Darmon-Taylor notes, or the next chapter of my notes, or Cornell, Silverman, Stevens. There's a bunch of places you can find this. Let me talk about some of the methods of proof. Method 1 is Schlesinger's criteria. So let C be a category of coefficient rings with residue field K. In Functors of Artin rings, the SFA paper, the author gives necessary and sufficient conditions for any covariant functor F from C to sets to be representable. That is, for there to exist a coefficient ring R equals R sub D and a universal element, we call it C equals C sub D in D of R, satisfying the universal property that for any coefficient ring A and any element alpha in D of A, so this functor output, there is exactly one ring homomorphism R to A, which is the identity on residue fields, and which sends the universal element C to alpha. So in other words, you have representability. Okay. So it's not too hard to imagine how you might use this criteria to actually get the result that you want, construct this actual universal deformation ring. We'll give a brief account of this later in this chapter. In Mazur's paper, Mazur proves that these criteria are actually met within the context of Theorem 1. So this is Mazur's kind of method of proof for the construction of the universal deformation ring, but it won't be our method next chapter. Method 2 is Falting's method. Faltings uses generators and relations. So Darman-Taylor notes talk about this. There's also the Lenstra and DeSmit method, which is the one we will use next chapter in chapter 9. And then there's the universal characters method, which we won't really talk much about at all. So Theorem 1 guarantees the existence of a universal character function along with the universal ring R acting as its value ring. And so then there's a proof of the construction of the universal deformation ring that deals in the converse to this idea, which again, we won't do much with, but I just want you to be aware that it exists. Okay, so starting next video, we'll begin looking a little more deeply into this concept. So I'll see you then. Thanks for watching.